Please sit down quickly. So let's start this session with Patrick Kelly that will tell us about the multiply image surrounding lens in Supernova Refsdal.
So I also wanted to say thanks to everyone organizing the conference, Mark, for providing me motivation for it. So I'm going to talk about Supernova Refsdal, which appeared in the fall of 2014, and it's actually still visible at HST now. So I'm going to talk about that first, and then I'm going to talk in the second half about a new transit which I think is actually equally exciting as Supernova Refsdal. And it actually is right in the same galaxy where Refsdal is working. So just as a background for the Supernova crowd about gravitational lensing. So if you have a background galaxy, and it happens to be behind a massive galaxy cluster, then the photons coming from the well-aligned galaxy will travel around both sides of the lens and converge on Earth, and then see multiple images of the same background source. So you can sort of think of this with a Fermat surface. So instead of having an index of refraction for an optical lens, you have a gravitational delay, and that comes in equal parts due to extra curvature of space and gravitational time dilation. So in fact, if you take the most direct route through the center of the lens, often you will actually arrive last when you compare your travel time to photons that take a more peripheral route. So back in the 1960s, gravitational lensing was really something of a backwater, and the only real detection of it was in the solar system. Sir Arthur Eddington and in the 30s, people sort of dismissed this as something we would never observe. And so, nonetheless, there were theorists who had given up thinking about it, and Sir Refsdal, the Norwegian astronomer, he thought about this possibility that a supernova might explode behind the gravitational lens, and we could see multiple images of it. He showed in this paper that if you had a good model for the lens and the matter distribution of the lens, from the time delays between the arrivals of the multiple images of the supernova, you could constrain the expansion rate of the universe, or conversely, if you knew H0, you could provide a very nice probe of the matter distribution in a lens. So you can just sort of see how you could do this. You know all the angles to images of a multiple image supernova, and you can measure this time delay, get C delta T, and then essentially you can establish an absolute distance scale. So it's a very different approach from, say, using clear linear supernova. Nonetheless, it was a long time for actually found one of these, and so Refsdal made this prediction in 1964. The first strong lensing system was this quasar that was discovered in 1979. It's actually quite bright in the sky. And people actually started using quasars to try to measure time delays and do time delay cosmology. But a multiple image supernova still wasn't found. And Pan-STARRS found a candidate, which was just a very bright type linear supernova that Robert Quimby followed up later with Peck and found evidence for a galaxy near or along the line of sight. So this may have been a magnetic type linear supernova, but there were no high-resolution images of it, so no evidence or multiple images were resolved. So it was in 2014 that we found Supernova Refsdal in the MAX 1149 galaxy cluster field. And there are multiple images of the host galaxy produced by the cluster. And so we're able to predict that it should reappear in the sky at a particular position in 2015, and that's what happened. So it's been an exciting couple of years. So as part of this Prism Lens Amplified Survey from Space that Tommaso Treo put together to basically use clusters as natural magnifying glasses and take prism spectroscopy of background sources, which can be at very high redshifts. So my role was to be the transient person, and we got together with the Frontier Supernova team, led by Steve, and a bunch of other people in the group, at the conference were part of this effort. And just searching through the data, and we're always happy to find one new transient. And then sort of one afternoon, I saw 4 sources, and the difference images was I sort of guessed what it probably was, and we certainly were not expecting to find one, so it was quite something. And in the next, we sent hundreds of emails in the next week or something like that, trying to figure out what this could be. There's no evidence for an AGN, and you can see here that it's not coincident. These sources aren't coincident with the nucleus of this spiral galaxy, so by definition, it's not a nuclear transient. And there happens to be this elliptical galaxy also in the cluster, which basically acts as a second lens. And so instead of seeing one image, you see 4 images at once here. So it's sort of doubly, multiply imaged, because the cluster produces multiple images of the host galaxy. This galaxy produces multiple images of this part of the spiral arm. And the galaxy is at a redshift of 1.5, and the cluster and the elliptical galaxy are at a redshift of 0.54. So we had a bunch of modelers on our team, including Zitrin, and so there were existing models of the galaxy cluster, and we knew that there were 3 images of this background galaxy, and could predict that the more peripheral image arrived first, probably sometime in the 90s, and then we detected this and said, well, we think it probably will appear again, in the next 5 to 10 years in our first paper, and then within the next week, multiple teams came out with additional predictions. They said that it will occur within, with the precision of a month, within a year from now. So the modeling community was very excited about this because it provides a blind test of something outside of the Milky Way and a new test of lensing models. So the time delay, so most models of galaxy clusters are constructed from the positions of multiple image galaxies, which depends on the derivative potential. The time delay depends on these derivative proportionals, differences in potential, and so it's a very different probe of models. So here's just a schematic showing the different paths taken by the light from the supernova. And here are some of the predictions from the community. And as you can see, a bunch of them were clustered here. So this is this is December 1st of 2014, and we detected it in early November of 2014. And so you can see it's about a year, all these predictions didn't all perfectly agree with each other. In fact, they were sort of distant with each other. So it was a nice test of different techniques that have been used to model galaxy clusters and use them as natural magnifying glasses to study galaxies going back to the organization. But supernova people were, of course, very interested in what kind of supernova it is. And if it were a type 1a supernova, of course, you could calibrate its absolute brightness or luminosity. And so we wanted to classify it and see if it was a type 1a supernova. So it was detected in November 2014, and fortunately the frontier field just started to observe the cluster, so we started getting this very deep photometry. And the early colors suggested it could be a type 1a supernova or a strict envelope supernova. And so we said, all right, let's get a spectrum of it. And so we asked the director, Matt Mountain. He said, okay, sure, we'll give you 30 orbits to get a prism spectrum. And so that's what happened. And in the meantime, supernova didn't start to fade as you would expect for a type 1a, but it kept brightening. And so I'll tell you more about that in a second. But basically, it kept brightening until around May of 2015, and we were able to get a second spectrum with X-Shooter, and then put together a program to continue monitoring the field after the frontier supernova orbits were all spent in cycle 23. So the community basically agreed that it should reappear in the next couple of years. So here's the light curve of Refsdal. So you can see it showed this slow rise for several months, or actually 6 months. And so, though this is not what you expect for a normal type 2 supernova or type 1A or a analog supernovae, and it turns out that it's like, or very much like 87A-like supernovae, and which has this distinctive slow rise. So, of course, we all know about 87A, which is kind of fun. So one of the most nearby supernovae, more distant, most distant supernovae, both seem to be 87A-like, and you might ask why the first Lent supernova is an 87A-like event. So perhaps the rate could be different in higher ratio. But here's the light curve of the 4 images in comparison to 87A-like templates. So it turns out there's one type 2N supernova that I could find that actually has a light curve quite similar to 87A-like events. So maybe an 87A-like event with some CSM. But in any case, we wanted to see whether, in fact, Refsdal could be a type 2N, and so that's where the spectra became very important. And you can see here also that in comparison with 87A-like, nearby 87A-like events, Refsdal is quite comparatively blue and also and luminous. And so that also begs the question of perhaps it could be a type 2N. And so we had all this wonderful risen spectra, and Gabe Rammer particularly did a great job extracting the spectrum. Along the trace is only about 10% of the total lights that model the nearby galaxies. So here's what we got for particle prism spectrum, and you can see we found statistically significant evidence for this P Cygni absorption feature in H alpha, and then probably also sodium D. This is a low signal noise spectrum, but we did very careful statistical analysis, and so these absorption features are not what you expect for a type 2N supernova, broad and deep absorption features. And so, and here's the X-shooter data from the ground. So we also see evidence for the probable evidence that's consistent with these absorption features. And then if you look at the H alpha strength of Refsdal and its evolution, it seems to agree with 87A-like, and this is O5CP, which is the 2N. So up here it seems to have stronger H alpha emission, and so there's this early non-detection from Mossfire, I think, which also is helpful in this comparison. So here is the absorption minimum H alpha, and so it shows reasonable agreement with what you might expect for a 87A-like event. So one thing might be possible if we try to calibrate it with something like EPM in a very rough way, but we haven't really had time to look at that in detail yet. So that's sort of what we've learned about the supernova so far, and it's still visible. And so we're working on the late time light curve, where we think there's probably evidence actually for microlensing from the stellar populations lens. One of the most exciting parts of this was that we could make this prediction that the supernova would reappear closer to the center of the lens. And so we think that we predicted the separation to be about 8 arc seconds away. And so the modeling community was very excited about this. And this is just one of the models that Claudia Grillo put together, which I think is pretty impressive, showing the model on the right and the HS team, which is on the left. And so you can even use the features of the galaxy itself to have very precise constraints on where to reappear and help model the local potential. So just a little bit of background about the models themselves and the techniques people use to model the mass distribution in galaxy clusters. And so you can have these various different kinds of profiles and different assumptions about the mass to light ratios of the galaxies. So people populate their clusters with matter depending on the luminosities of the galaxies in the cluster. And then there are all sorts of sort of less parametric techniques. And so you also, generally people assign an anisotropy profile to the cluster, so a larger scale, cluster scale anisotropy profile. Other people have sort of less parametric approaches, like Adi has this light traces matter, and Chima Diego has a superposition of many gadgets. So you'll see some of these models, and I think these different techniques actually account for most of the differences in predictions. And so here are some of the models of just the elliptical galaxy that produces the 4 images of the supernova. So you can see some of the differences among the time delay sequences. So we did a first analysis with the 4 images and compared the predicted time delays to what we saw in the multiple and the sort of relative magnifications or luminosities of the supernova. And so the model did fairly well. It wasn't perfect agreement, so I think there's a lot to learn there. And so we thought that the supernova, most of the community suggested it probably should arrive by October, and so the field comes out from behind the sun in October. But in the first few visits, we didn't see anything, and so I was starting to worry a little bit about the model for the modelers. But we just were patient, and in December we saw some light sort of close to where we expected, and then we kept bidding images, and sort of by March, very significant evidence for a reappearance. And so from this early data, we were able to first compare with the predictions for where it should reappear. And so the Griot model seems to have done a terrific job here. And this is partly just because there are a lot of H2 regions in the spiral galaxy, so that really helps. So it should appear the same place in the galaxy. So from this early data, we were able to put sort of degenerate constraints on the time delay and the magnification, which we're now working to improve. So we have another 30 orbits of data, and so we've already basically ruled out a lot, probably a fair number of these predictions, and community can work on trying to interpret what we've been able to learn. You can see here that if you use different sets of galaxies, you can get some different some variance, but a lot of this variance seems to be due to different modeling techniques. And so you can see here that this is Adi's light traces matter, Chima's, and then we found a software bug, or one of the teams found a software bug in the program. So I think we're looking forward to learning about modeling techniques and and so just to sort of summarize what we learned about Refsdal, and I'll talk about this also very exciting transient. This is the first multiple image supernova with resolved images, and we now know it's an 87A-like explosion, which is interesting. And nearby universe, of course, they seem to prefer low metallicity environments, and so perhaps they're more common at higher redshifts. And of course, the magnification helps us look for objects that we might not otherwise be able to detect. And so we've also been able to make the first prediction of appearance of a supernova at a position and time on the sky, which is fun, and working on testing these mass models. So we have another visit even in October, so we should be able to keep following the light curve for at least several more months. So now I'm going to switch over to another object which appeared actually in the same galaxy a few months ago, and it's worth keeping in mind that this is sort of the first time we've been able to look at a galaxy cluster for multiple years with Hubble. And so, in some ways, the follow-up campaign has sort of been an unprecedented observing campaign as well. So you can see here the image of sort of where Refsdal appeared around this elliptical galaxy, and then this is where the reappearance occurred, and so this is the one that appeared in December. And then in late April, a news source showed up right here, and so this is kind of an interesting position on the in the galaxy cluster, and so we've sort of followed this up for with the Refsdal redox orbits, and then some frontier supernova data, and then a director's discretionary program. And sort of what's interesting about it is that it seems to be perfectly aligned with what's called the cluster's caustic. or critical curve, and this is where the magnification of a sort of hypothetical point source becomes infinite. And so, in general, in lensing, the galaxies that are lensed by clusters, or planets that are, stars that are microlensed are much larger than the size of this caustic curve. And so you can get total magnifications up to, say, 100. But in this case, a star behind a galaxy cluster is just about the right size that you can get magnifications perhaps up to 10 million. So this is something that Jordi Morales-Gude sort of predicted or considered back in 1981, but has never been observed. So I think the paper has something like 5 citations. And so this is what this got us very excited. And so we were able to look at, try to learn more about it. And so here's just the location on a color image. And so it's kind of along this elongated bluer region of the host galaxy. So here's one image of the host galaxy, here's another, and then this critical curve lies in between them. So it's coincident with what appeared to be a knot in the clash and the frontier field data. So here I'll just show you also that here's this is sort of what the critical curve might look like for a galaxy cluster, and this is something Chino put together. And another sort of interesting fact here is that if you have all of the dark matter in the universe as primordial black holes, these black holes should disrupt the caustic, and so we actually wouldn't expect to see something like this. And so we're trying to interpret this event perhaps and use it to place limits on primordial black hole limits. So here's partly why we think it's a star. It's because it has this Balmer break, and you can model it fairly well with an solar atmosphere of about 13,000 Kelvin. This is not something that I'm aware of often see in normal transients. Like supernovae or LBVs, and so this seems to be good evidence that it's actually a B star. It's the right redshift. And so here's the light curve we observed, and so it shows this slow. This is over I guess like the last year, and so you can see this slow rise and then a sharp decline, and that's what you expect. If you have the stars moving behind the caustic curve, you have two images, and they become extremely elongated, and then they're destroyed, and so then the transient should just disappear within a day or hours, depending on the size of the test. And here's a model. There's one sort of earlier uptick here, which we think may be due to microlensing. In this case, Chima is modeling it as a Jupiter-sized planet. So anyway, so this is, we haven't been able to come up with equally good heating theory, so this is what we're working with right now. And so this is also a very fun transient, and it goes back not 50 years, but 25 years to the original prediction. So hopefully with more cluster monitoring campaigns, we can find more of these and study individual stars at cosmological distances before they explode. It's a lot of fun. Thanks.
Questions?
So for the candidate constant crossing event, you will, if it's a star, you will expect to see color change on the do you see what is?
Yeah, so that's right. So for gravitational lensing in general, you wouldn't expect a color change. And so, on average, we don't see the color seems to not change very much. But of course, there's stuff like limb darkening. So if you're at the limb, the caustic curve is right on the limb darkening, you might expect some color change because you expect a redder color at that point. So there could be binaries, but so that we're still working on photometry. But on average, there doesn't seem to be much of a change. A couple of possible exceptions.
More questions?
Are you concerned on the source effect? So these source release versus annualized release usually? finite source effect.
Yeah, so like,
What's the constraint on finite source effect?
so this is, you mean, you're referring to like Hempdale lensing? And,
No, if you have a cosmic crossing, if you point source, it will infinite magnification. Right? You never have point. There's a source set. On cosmic crossing, you can measure the angular ratio, angular size ratio between the source and Einstein radius from the width of the.
yeah, right. So how quickly the transient phase is very very sensitive to the radius of the star itself, as well as the peak magnification. So we're working on trying to interpret the Lake curve in terms of the stellar radius and its transverse velocity.
I can just yell. So how many of these events do you expect from this particular caustic? You just keep looking at it.
So the only work that's been published on this is from Dre's original paper, and so he calculated something like you would expect for any given arc, one of these reaching like E-band 25th magnitude every 5 years. So I mean, this is a long time. There are other people on our team like Kaiser who think the rate should be extremely low. So I think there needs to be more work on that. But it's not crazy. If you add the time spent with the Refsdal follow-up with frontier fields and Flash, then 5 years. But I mean, there's multiple arcs. So.
We have time for one more question. If not, let's thank Pachi again.